Have you ever looked up at the night sky, twinkling stars, silent, drifting moon, and wondered if you could just climb up there? Imagine an elevator, not one that takes you to the top floor of a skyscraper, but one that takes you all the way to space. A ribbon stretching from the Earth's surface past the clouds beyond our atmosphere into the silent black void. This isn't just a scene from a movie. It's a concept scientists and engineers are seriously thinking about. It's called a space elevator, and it could completely change our relationship with the cosmos. It's an idea so big, so wild, it almost sounds like magic. But is it? Where do big ideas like the space elevator come from? Well, like so many of our greatest technological ambitions, this one started in the world of imagination, science fiction. The first person to really lay out the idea was a brilliant Russian scientist named Konstantin Tsiolkovsky. In 1895, after being inspired by the newly built Eiffel Tower in Paris, he imagined a tower so tall it reached all the way into space. He called it a celestial castle. He even figured out that the top of this tower would have to be in what we call geostationary orbit, a special spot where an object orbits Earth at the same speed the Earth spins. This way, the top of the tower would stay over the same spot on the ground. It was a revolutionary thought. For many decades, the idea remained mostly in the realm of stories. Science fiction writers loved it. One of the most famous examples is Arthur C. Clarke's 1979 novel, The Fountains of Paradise. In his book, engineers build a space elevator on a mountaintop on a fictional island. Clarke's writing was so detailed and so scientifically grounded, it brought the concept to a huge audience and made a lot of people, including scientists, take a second look. He made it feel real. He explored not just how it would be built, but how it would change society, politics, and humanity's future. All right, so how would this thing actually work? Let's get rid of the complicated math and just think about the big picture. Imagine you have a very, very, very long piece of string. You tie a rock to one end and start swinging it around your head. As you swing it faster, the string gets tight, right? The rock wants to fly away, but the string holds it in place. Now imagine your head is the Earth. The rock is a giant counterweight, like a captured asteroid or a big space station, and the string is our super strong space elevator cable. The Earth is spinning, and this makes the counterweight swing around it, pulling the cable taut. The cable is so long that the counterweight is in geostationary orbit, 35,786 kilometers, about 22,236 miles up. Now we have our track to space, a super strong ribbon, maybe a meter wide but thinner than a piece of paper, stretching from an anchor station on the Earth's equator, all the way up to our counterweight. So how do you ride it? You wouldn't step into a normal elevator car with buttons for different floors. So if the idea is so simple, why don't we have a space elevator already? Well, we've run into a few small problems. The biggest one is gravity. The Earth is constantly pulling on the elevator's cable. To build a structure that's over 35,000 kilometers tall, you need a material that is unbelievably strong, incredibly lightweight. The cable has to be strong enough to support its own immense weight, plus the weight of the climbers going up and down it, all while being pulled by Earth's gravity. It's a challenge of material science unlike any other. For a long time, we simply didn't have anything that could even come close. Let's put this in perspective. Steel. If you were to make a steel cable and hang it, it would snap under its own weight after just a few kilometers. It's just too dense. Titanium, Kevlar. Getting better, but still not good enough. Scientists calculated the specific strength. That's a measure of a material's strength divided by its density that would be needed. The number they came up with was enormous, far beyond any material that existed for most of the 20th century. For decades, the space elevator was stuck on the drawing board because the magic material it required simply did not exist. It was a showstopper. Then, in the 1990s, came a breakthrough: carbon nanotubes, and later, graphene. These are forms of carbon, the same element that makes up diamonds, pencil lead, but arranged in a very special way. Carbon nanotubes are like tiny, rolled-up sheets of chicken wire made of carbon atoms. They are one of the strongest materials we have ever discovered. Graphene is a single flat sheet of those carbon atoms arranged in a honeycomb pattern. In theory, they are both incredibly light and mind-bogglingly strong. On paper, they have the specific strength needed to build a space elevator ribbon. Let's say we solve the material problem. We can now produce a giant spool of our super strong carbon ribbon. How in the world do we actually build the space elevator? You don't build it from the ground up. The leading plan is to build it from the top down. It would start with a conventional rocket launch, a big one. The rocket carries the initial spool and a construction satellite to geostationary orbit, 35,786 kilometers up. Once in position, the satellite begins to unspool the ribbon, lowering it toward Earth. As the ribbon unspools downwards, the satellite must also unspool something upwards. It unspools another ribbon or a heavier mass outwards, the counterweight. Why? It's all about balance. Think of a seesaw. Lowering the ribbon pulls on the satellite and can drag it out of orbit, so you extend mass the other way to compensate. The center of mass, ribbon going down, ribbon going up, satellite in the middle, must stay in geostationary orbit. Once anchored, construction can truly begin. The first climber is sent up the ribbon. It carries no people. It's a construction vehicle carrying more ribbon material. As it climbs, it attaches a new layer alongside the first, thickening and strengthening the cable. More climbers follow, each adding another layer until the ribbon can handle regular traffic. But even this plan is filled with dangers. The ribbon is a giant target. It must pass through the atmosphere and face wind, lightning, storms. Higher up, it must contend with space debris, thousands of tiny, man-made objects from old satellites and old rockets zipping around at incredible speeds. Even a small fragment could sever the ribbon. Then micrometeoroids, tiny bits of rock from space. The elevator needs ways to dodge larger debris. So, with all these challenges, is anyone actually trying to build a space elevator today? The answer is yes, but in very small, careful steps. We are a long way from unspooling a ribbon from orbit, but important research is happening all over the world. Right now, the biggest focus is on that magical material we talked about, carbon nanotubes. Scientists in labs are working tirelessly to figure out how to produce longer, stronger, more perfect strands of this material. They are experimenting with different manufacturing techniques, trying to move from creating microscopic specks to producing usable fibers. Every improvement, every centimeter of stronger nanotube fiber they create, is a step toward the space elevator. There have also been real-world experiments and competitions to encourage innovation. For many years, NASA sponsored a competition called the Space Elevator Games. These games challenge teams to build strong tethers and working climbers. Climber competition. Machines climbing a cable suspended from a helicopter or a crane, powered only by a beam of light from the ground. These were small-scale demonstrations, but they proved the basic principles of power beaming and climber mechanics could work. In 2018, Japanese researchers from Shizuoka University took a tiny step into space. They launched a test satellite to the International Space Station called STARS-Me. The experiment consisted of two tiny 10-centimeter cube satellites connected by a 10-meter-long steel cable. A small motorized climber box, designed to look like an elevator car, was meant to travel along the cable. While the test had some difficulties, it was the very first time in history that an object had moved along a tether in space. It was a symbolic, but important proof of concept. We've journeyed from a wild idea to the nitty-gritty science, from science fiction dreams to real-world experiments. So what's the verdict? Will we ever build a space elevator? The honest answer is, maybe. It is not, as far as we know, impossible. There are no fundamental laws of physics that say it can't be done. The challenges are not matters of science, but matters of engineering. They are enormous, mind-bogglingly difficult engineering problems, but engineers are very good at solving problems. If we can solve the material science puzzle and figure out how to mass-produce a carbon nanotube ribbon, the biggest hurdle will have been cleared. If we do build it, the impact would be world-changing. The cost of sending things to space would plummet from tens of thousands of dollars per kilogram on a rocket to perhaps just a few $100s. This would spark a new golden age of space exploration. We could build massive solar power stations in orbit that beam clean energy down to Earth. We could mine asteroids for precious resources that are rare on our planet. We could build large-scale habitats in space or on the Moon and Mars far more easily. Of course, The timeline is a huge question. The most optimistic experts think we might see the beginnings of a space elevator in the next 50 years.